Thank you very much for the introduction, Maggie, and Pinfa North America for organizing the webinar to speak to you about fire protection materials for EV batteries. So before we get started, I'd like to run through a quick introduction to IDTechEx for those who aren't aware who we are. So it's obviously the company I work for. We're essentially a market research firm, but with a focus on emerging technologies covering a wide range of areas, including advanced materials, energy and decarbonization, sustainability, electric vehicles, semiconductors, computing, robotics, and many, many more. As you can see on the slide here, IDTechEx also provides in-depth technology assessments, scouting, and company profiling through primary research, using and also using our in-depth understanding of markets and insights. We also provide market reports and forecasts and provide strategic advice through those reports. So at IDTechEx, we provide technical insights and market understanding with over 250,000 global contacts, which we leverage for primary research and interviews with a focus on technology innovations and their applications across essential industries. So onto the topic of today. So this presentation is based on IDTechEx's fire protection materials for electric vehicle battery report, which covers adoption of these materials, regulations, insights into cell formats and cell-to-pack battery structure, material benchmarking, market forecasts for each segment, and lots of company profiles for companies developing these materials with use cases from OEMs and supply chains. So today I will leverage analysis from the report and ongoing coverage of the area to highlight some of the thermal runaway regulations, cell chemistry, cell formats, and cell-to-pack battery structures, go over some of the options and examples of fire protection materials that are used for EV batteries, go over some of the examples of material benchmarking that we have conducted in-house to show how they compare with each other, and then can also cover how material choice can aid the overall battery design and give you some insights into market share predictions as well. So as a quick overview of the EV market for battery and plug-in hybrids, you can see on the chart that the market has grown strongly over the last few years. Some countries and regions have seen stronger growth than others, like the significant growth in EV sales in China, but also growth in Europe and US as well. Although there has been some turbulence in the last year, especially in the US. But the overall narrative is that in the short to medium term, growth is expected, but probably not to the extent previously expected by some. But we expect the market to continue growing, driven by emission regulations, greater consumer acceptance, and also imposed combustion engine bans later into the next decade. So thermal runaway. Thermal runaway of lithium batteries is a key topic for electric vehicles. Particularly notable fire events have occurred globally, with examples including large automotive recalls, electric bus fires, scooter fires in India, and also, stationary energy storage fires. And in electric vehicles, increasing energy density, cell-to-pack or cell-to-body designs, fast charging, and keeping battery costs low all impact the fire protection considerations for EV batteries. And with evolving standards and growing, EV market, there is an increased focus on thermal runaway prevention, fire protection, and providing longer escape times for passengers. So this presents a huge opportunity for several types of fire protection materials. So now I'd like to provide an overview of the thermal runaway regulations for electric vehicles, as these are a key driver for adoption of fire protection materials. China was, the first to implement thermal runaway specific mandate in the China GB 2020 standards, which were implemented at the beginning of 2021. So there are lots of factors that go into it, but a key factor that people may be aware of is the 5-minute warning that is mandated, which is essentially from the start of a thermal event, you have to give the occupants 5 minutes before any fire or smoke exits the pack to allow occupants to exit the vehicle. And this is far from perfect. For example, there's a lot of cells that will vent gases in the event of a thermal runaway. And these gases are not visible, which doesn't play into the no fire or smoke visible outside of the pack. And actually, these gases can be volatile, for example, hydrogen or carbon monoxide being released. So that side of things may be more of a focus for future regulations. But the rest of the world is yet to fully mandate thermal runaway standards. They are mentioned in the UNECE regulations, but not fully integrated into regions yet. And essentially, they're still under development. One standard that isn't mentioned here is for India is the AIS 156, which essentially requires battery packs to prevent thermal runaway propagation, essentially requiring the battery pack to contain any fire or explosion from the thermal runaway, which is putting a lot of emphasis on materials used for thermal barriers to aid the prevention of propagation and enhance battery management systems. One thing that has been a challenge is that as battery designs are so varied vehicle to vehicle, it has proven very difficult for regulators to keep up with the developments that are happening in the battery space. And the key takeaway, I suppose, is that future regulations are likely to have a longer escape time, more attention paid to gas generation and detection, and also, when systems do fail, the mechanisms through which they fail. And actually, we are seeing updated regulations come through with stricter requirements. So back in April 2025, it was announced that China's GB 38031 2025 would be mandated by July 2026 for new vehicles. So this 2025 update goes well beyond the previous one, with the requirement for no fire or explosion for 2 hours after the initial event. And the warning to the vehicle occupants is still present, and no visible smoke should enter the passenger compartment within 5 minutes of the event. Europe is looking to the UNECE R100 standard and its changes. The R100-05 version is set for implementation for new vehicle types in September 2027 and all vehicles by September 2029. This is significantly behind China's 2026 implementation and has requirements that are much more similar to China's 2020 standard. And in the US, the latest versions of the FMVS S305A closely follows the UNECE regulation, but has taken a less stringent standard for safety. So here there's no need to detect single cell thermal runaway, but it is completely based on the temperature within the pack. So now with the regulatory scene in mind, I'd like to spend some time looking at the trends in battery design and cell chemistry, as these all impact the level of fire protection required and the choice of protection materials. So the three main cell formats for electric vehicles, we have cylindrical cells, prismatic cells, and pouch cells. And you can see on the chart here, All three remain popular. So there's little indication at the moment of the automotive industry settling on a specific cell form factor, and all three remain popular. Prismatic cells are extremely common in China. Pouch cells continue to be popular with LG Chem and SKI customers such as GM, Ford, and VW. Whilst Tesla were the key player using cylindrical cells and now using prismatic LFP cells in standard range variants, BMW has adopted for cylindrical cells for its sixth generation drivetrain. But the key thing to note is that cell formats, it has a significant impact on the pack density, and each cell type having its own set of benefits and challenges, and each OEM taking its own approach to designing battery packs that build its flexibility to diversify its supply chain. Now, looking at the battery chemistries, these can impact, the energy density, cost, and also the fire safety. So on the chart, we're looking at historic trends in lithium-ion battery cathode chemistry for battery electric vehicles with data collected from IDTechEx. And you can see that there have been shifts between adoption of different chemistries. So currently, the market remains dominated by high nickel layered oxides, like NMC, NCA, LFP, and also mid nickel layer oxides to a lesser extent. But with high nickel layered oxides and LFP, these are expected to dominate over the next decade. We also expect demand for LFP to grow due to reduced costs, higher safety, and technological innovation, improving pack and system level energy density. And lastly, we also expect mid-level nickel layered oxides to be phased out in favor of high nickel variants for many electric vehicle segments. Now moving on to how battery packs are assembled, a traditional EV battery consists of many battery cells that are combined together to form a module. In turn, these are combined together inside the battery enclosure to form a pack. However, a key trend in the EV battery industry is towards greater packing efficiency, with the aim of improving energy density whilst reducing complexity and cost. Simply put, we want more of the battery to be taken up by the cells rather than all the components that do not actually store energy. And a key step change here is cell-to-pack designs. And in cell-to-pack designs, we remove the modular structure and have all the cells packed directly together to form the pack. And this reduces the number of components, leading to simpler manufacturing and reduced costs. And this approach has been deployed by players such as BYD, CATL, Tesla, and several other players, with more planning deployment in the future. Cell to body or cell to chassis takes this even further by making the battery pack an integral part of the vehicle structure. I've already mentioned some of the advantages in that you have fewer parts, higher energy density, but you can also have simplified thermal management and manufacturing to lower costs. But it comes with challenges. So, specifically, it becomes more difficult to contain thermal runaway as you no longer have the individual battery module covers or enclosures. So this adds more burden on the fire protection materials themselves. This is in addition to other repercussions, including, difficulties in servicing and recycling, poorer crash resistance, and also some loss in mechanical integrity. But the key advantage is the higher energy density, which I alluded to. So on the chart here, you can see a comparison of the cell to pack ratio for 31 battery electric vehicles on the market from IDTechEx database for cell to pack and cell to module pack designs. Generally, cell to pack designs present a much better cell to pack ratio. So this is the amount of the pack which is taken up by the cells themselves. So to give you numbers, on average, in modular designs, 62% of the battery pack weight is accounted for by the cells. Compare this to 84% in cell to pack designs. In essence, cell to pack concept makes much better use of the weight and volume available. So now we'll move on to look at some of the fire protection materials and where they are used within the battery pack. So just a quick overview. Depending on where the fire protection materials are added, they have different roles and functionalities. And there are different options for the materials because you can apply them outside of the enclosure, you can apply them inside the enclosure, apply them between the cells, or even outside the modules themselves. Typically, the most common approach so far has been applying sheets of materials above the modules, but of course, this is very dependent on the manufacturer. But also for cylindrical cells, encapsulating some of the materials that go between the cells is also quite common. If we're going to be applying the material at the enclosure level, might need to start thinking about materials with EMI shielding, but also provide structure and prevent fire propagating outside of the enclosure. For materials between the cells, need to think about thermal and electrical insulation, some degree of conformability to conform to the cells, may also need to provide some structure for the cells as well, so especially for cylindrical cells. But the key thing is all of this is very OEM dependent. So, and it's also dependent on the battery design, and everyone has a different approach to putting together a battery pack. So there's a lot of opportunities for different materials. So to kind of give you an idea of some of those materials, here I've highlighted some of the different materials used in the market and whether they are, and where they are used between the cells or at the pack level protection. So for cylindrical cell systems, encapsulating foams are extremely common. We've seen in a lot of two-wheelers, more traditional thermally conductive encapsulants like potting to be used. But with the newer test methods like those in India, like the AIS 156 I mentioned earlier, we are seeing more adoption of things like phase change materials or even some of the polymer cell holders, which can provide some structure to the cells, but also some fire protection. And at the pack level, ceramic blankets and mica sheets have been very common, basically applied at the top of the modules or below the lid, like we're now seeing, we're seeing a lot of interest in other materials like aerogels that have very low thermal conductivity and also are very lightweight, which is why the market has grown very rapidly within the last few years. And then on the outside of the pack, or some of the internal components, we see more typical fire protective coatings like powder coatings or even intermescent coatings where the material expand when exposed to fire. It's also worth noting at this stage that there is quite a bit of overlap between some of these categories as well. So for example, a lot of the polymer solutions will include phase change materials or intermescent coatings. And for instance, aerogels may be encapsulated in something else to overcome some of the challenges around dust, for example. In our report, we have talked to a huge number of companies operating in this space and gathered various parameters for their products. And in our database, we have just under 200 materials from 72 companies of different materials being used or being advertised for EV battery fire protection. So you can see there's a lot of different companies operating in this space. Some of these companies are repurposing existing materials from insulation materials or other applications such as industrial or construction, or many have come up with brand new materials that are specially designed for EV batteries, mainly because the requirements are different, or the temperatures are much higher, and the volumetric and gravimetric density are also very critical for EV batteries and not so much for some of the other applications. But we do provide more comprehensive comparisons and give the list of all the companies and access to our company profiles with the report. So this is some of the data I'm showing categorized by material categories. So the actual selection of material will depend on the design of the battery. So in earlier designs, it was somewhat of an afterthought, just applying something on top of the module, for instance. But in newer designs, it's becoming a much earlier consideration in the battery design. So looking at the chart, we're showing a couple of key properties. So you can see why aerogels are becoming very popular and getting a lot of attention in terms of their very low thermal conductivity and the density. But the chart itself doesn't tell the entire story. So, for example, some of these materials may be multifunctional or replace other materials. So even if their density looks higher in comparison in this chart, if they are replacing something like a cell holder or some electrical insulation, then replacing those materials can offset some of the issues with the density. And that will become, more apparent when you do costing as well. Some of these are also more thermally conductive than others, which will depend on the design of the battery. For example, in some of the two-wheeler applications that don't have an active cooling, then potting or encapsulant materials are more common, or more recently, phase change materials, as I mentioned earlier. These are more suitable because without active cooling or thermal management systems, there is greater burden on the material to spread out that heat more effectively. And one of the materials I want to cover in a little bit more depth, which is growing in adoption for EV batteries in recent years, is aerogels. So these materials are ultra lightweight and highly porous. And this is actually a material that initially found applications in building and construction, in industrial applications, in LNG or energy, oil and gas pipelines, but have in the last few years found applications in electric vehicles as well. So the majority of aerogel solutions for EV fire protection are actually based on silica or silica composites. And depending on the type of these material or composite, for example, some fibers used are ceramic, while others are mineral or polymers. These can have maximum operational temperatures that range between 350 degrees Celsius to up to 1300 degrees Celsius. Anyone familiar with aerogels will already know a key challenge with silica composites or silica aerogels in general is that they liberate a lot of dust, which not only makes the handling challenging, but it also can affect the performance over the lifetime. So manufacturers often get around this with encapsulation. On the other hand, you also we're starting to see developments of dust-free polymer aerogels and polymer composite aerogels emerge, although the maximum operational temperatures of these materials don't typically exceed 300 degrees Celsius. And they're also more expensive, so they have more niche applications. But essentially, these materials, in some cases, can carbonize when exposed to high temperatures and can also function as ablative coatings in specific cases. Another thing to consider is that polymer aerogels have a significantly lower density than silica composites. So these have particular suitability for eVTOL, aerospace, satellite applications, for instance, rather than in electric vehicles. And as part of our research, IDTechEx spoke to players in the field such as Aerogel Technologies, Blue Shift, who are developing polymer-based aerogels. And some of the players are also looking at developing compressible aerogel solutions by compositing aerogels with porous polymer matrices that can not only demonstrate compression performance during battery charging and discharging cycles, but also can prevent thermal runaway propagation at a third of the weight of typical silica composite counterparts. So just to show some of the other analysis we've done within IDTechEx, this chart looks at how much material is going to be needed for a cylindrical pouch or prismatic battery per kilowatt hour of battery, because obviously it is no use using a super light material if we need to use a lot of it. So looking at this comparison, similar to a chart a couple of slides ago, you can see why aerogels and encapsulating foams are quite popular or gaining interest because of their really low material intensity. But it doesn't necessarily convey the entire story, specifically for materials that have multifunctionality, for instance, which can replace some other materials. So, for example, polymers are quite popular in two-wheelers where you can replace multiple materials with a single one. So looking forward into the future, we are expecting some of the traditional materials like mica, foam, traditional coatings, ceramic blankets, and encapsulants to remain in the market, but they're not going to, they're not going to be eliminated by any means. But we are seeing interest and growth in some of the emerging materials like aerogels, polymers, compression pads with bioprotection, phase change materials, and intumescent coatings. And obviously, each of these materials have their own pros and cons that depend on the battery design and cell format. And in our report, we do break this down into different material categories and forecast them individually and also benchmark them individually. But with the overall growth of the EV market and the incoming regulations, we do expect growth of all material categories that we forecast in the report, but at different levels. So this was a quick overview of the market and some of the analysis we have in the report and the coverage within IDTechEx on fire protection materials for EV batteries. So to summarize, EV cells continue to grow, but there are regional narratives that dictate the growth moving forward. We also have regulations that have been employed for fire safety, with more stringent regulations coming in, such as those from China. And this is specifically key as EV design cycles is typically around 3 to 5 years. So OEMs and material providers need to stay ahead of the game in keeping up with upcoming regulations and bring material considerations very early on in the design cycle. There are also, various locations where fire protection materials can be applied, as I've shown earlier, and where the materials are placed will have different requirements. There are also a huge number of material types and companies within the field, and is getting increasingly competitive. But within each category, there is still room for innovation and differentiation. And a key area of differentiation is where a single material can replace multiple materials in the battery pack. And lastly, a lot of the incumbent options are likely to remain in a large way, but emerging materials will experience significant growth and have already started to do this, is already on this trajectory. And with that, thank you for the attention. And if you'd like to know more about IDTechEx research and services, then please feel free to reach out via the contact details shown on the slide. You can also reach me via the contact details shown here.